Good evening, ladies and gentlemen. How is everyone doing this evening? That is good to hear. So, last week we ended off with the formation of stars. So, we looked at how low mass stars form, we looked at how high mass stars form, and we know where they all fit in on the HR diagram. And now we're going to see and start looking at what happens at the end of the life cycle of stars. So what happens when they all eventually die out? So to get a better understanding of what this lecture is about and to understand this tonight's lecture and tomorrow night's lecture better, I'm going to show you three short videos of the work we are going to cover.
Stars are in a constant struggle between gravity trying to collapse them and their internal heat trying to inflate them. For most of a star's life, these two forces are at an uneasy truce. For a star like the Sun, the balance tips in its twilight years. For a brief, glorious moment, it expands, but then blows away its outer layers, leaving behind the gravitationally compressed core. It goes out with a whimper. Well, a whimper from a 2 octillion-ton, barely constrained nuclear-powered fireball. But more massive stars aren't quite as resigned to their fate. When they go out with a bang. A very, very big bang. In the core of a star, pressure and temperature are high enough that atomic nuclei can get squeezed together and fuse. This releases energy and creates heavier elements. Hydrogen fusion makes helium, helium fusion makes carbon, and each heavier element, in general, takes higher temperatures and pressures to fuse. Lower mass stars like the Sun stop at carbon. Once that builds up in the core, the star's fate is sealed. But if the star has more than about 8 times the Sun's mass, it can create temperatures in its core in excess of 500 million degrees Celsius, and then carbon will fuse. There are actually a lot of steps in this process, but in the end you get carbon fusing into neon, magnesium, and some sodium. What happens next harkens back to what we found goes on in the Sun's core as it ages. Fuse an element, create a heavier one, then that heavier one builds up until the core contracts and heats up enough to start fusing it. So carbon fusion makes neon, magnesium, and sodium, and those accumulate. The core heats up, and when it reaches about 1 billion degrees, neon will fuse. Neon fusion creates more magnesium as well as some oxygen. These build up in the core. It shrinks, heats up to about 1.5 billion degrees, and then oxygen fuses, creating silicon. Then that builds up until the temperature hits about 2 to 3 billion degrees, whereupon silicon can fuse. Among a pile of other elements, silicon fusion creates iron, and that's trouble. Big, big trouble. Once silicon fusion starts, the star is a ticking time bomb. But before we light that fuse, let's take a step back. What's happening to the outer layers of the star? What do we see if we're outside, looking back at it? Because the star was born massive, it spent its hydrogen fusing days as a blue main sequence star. Stars like this are extremely luminous and can be seen for tremendous distances. Like the Sun, though, a massive star changes when hydrogen fusion stops. Its core contracts, and then helium fusion begins. It swells up just as the Sun will, but instead of becoming a red giant, it generates so much energy, it becomes a red supergiant. These are incredibly huge stars, some over 1 billion kilometers across. and they are luminous. For example, Betelgeuse in Orion is a red supergiant and one of the brightest stars in the sky, despite being over 600 light years away. From that distance, you'd need a decent telescope to see the sun at all, and that's nothing compared to VY Canis Majoris, the largest known star, which is a staggering 2 billion kilometers across. We even have a special term for it, a hypergiant. As the core switches back and forth from one fusion reaction to the next, the outer layers respond by contracting and expanding, so a red supergiant can shrink and become a blue supergiant. Rigel, another star in Orion, is a blue supergiant, putting out over 100,000 times as much energy as the sun. Okay, let's go back to the core. It now looks like an onion with multiple layers. Iron is building up in the center, surrounded by fusing silicon. Outside that is a layer of fusing oxygen, then neon, then carbon, then helium, and finally hydrogen. You might think massive stars would last longer because they have more fuel than lower mass stars. But the cores of these monsters are far hotter and fuse elements at far higher rates, running out of fuel more quickly. A star like the sun can happily fuse hydrogen into helium for over 10 billion years. But a star twice as massive as the sun runs out of hydrogen in just 2 billion years. A star with 8 times the sun's mass runs out in only 100 million years or so. And each step in the fusion process happens faster than the one before it. In an extreme case, like for a star 20 times the mass of the sun, it'll fuse helium for about 1 million years, carbon for about 1,000, and neon fusion will use up all its fuel in a single year. Oxygen lasts for only a few months. Silicon fuses at a ridiculously high rate. The star will go through its entire supply in, get this, a day. Yes, 1 day. The vast majority of a star's life is spent fusing hydrogen. The rest happens in the metaphorical blink of an eye. Silicon fuses into a bunch of different elements, including iron. That inert iron builds up in the core, just like all those elements did before. And just like before, the iron core shrinks and heats up. But there's a huge difference here. In all the previous fusion stages, energy is created. That energy transforms into heat, and that helps support the soul-crushing amount of stellar mass above the core. But iron is different. When it fuses, it actually sucks up energy instead of creating it. Instead of providing energy for the star, it removes it. This accelerates the shrinking, compressing the core, heating it up even more. Even worse, at these temperatures and pressures, the iron nuclei suck up electrons that are whizzing around, which are also helping support the core. It's a double whammy. Both major means of support for the star are removed in an instant. Silicon fusing into iron is happening so fast, this literally takes a fraction of a second once it gets started. The core gets its legs kicked out from under it. It doesn't shrink, it collapses. The gravity of the core is so mind-bogglingly strong that the outer parts crash down on the inner parts at a significant fraction of the speed of light. This slams down on the central core, collapsing from several hundred kilometers across down to a couple of dozen kilometers across in just a few thousandths of a second. The star is doomed, because all hell is about to break loose. Now, at this point, one of two things can happen. If the star has less than about 20 times the sun's mass, the core collapse stops when it's still 20 or so kilometers wide. It forms what's called a neutron star, which I'll cover in the next episode. If the star is more massive than this, then the collapse cannot be stopped by any force in the universe. The core collapses all the way down to a point. The gravity becomes so intense that not even light can escape. A black hole is born. We'll cover black holes in a future episode as well. But for now, what happens when the core collapses and suddenly stops? The core of the star, whether it's a neutron star or a black hole, is now extremely small with terrifyingly strong gravity. It pulls on the star's matter above it hard. This stuff comes crashing down at a fantastic speed and gets hugely compressed, ferociously heating up. At the same time, two things happen in the core. While this stuff is falling in, a monster shockwave created by the collapse of the core moves outward and slams into the incoming material. The explosive energy is so insane, it slows down that material substantially. The second event is that the complicated quantum physics brewing in the core generates vast numbers of subatomic particles called neutrinos. The total energy carried by these little neutrinos is almost beyond reason. In a fraction of a second, they carry away 100 times as much energy as the sun will produce over its entire lifetime. That's an incredible amount of energy. Now, these little beasties are seriously elusive and hate to interact with normal matter, One single neutrino could pass through trillions of kilometers of lead without even noticing. But so many are created in the core collapse and the material barreling down on the core so dense that a huge number of them are absorbed. This vast wave of neutrinos slams into the oncoming material like a bullet train hitting a slice of warm butter. The material stops its infall, reverses course, and blasts outward. The star explodes. It explodes. This is called a supernova, and it is one of the most violent and terrifying events the universe can offer. An entire star tears itself to shreds, and the expanding gas blasts outward at 10% the speed of light. The energy released is so huge, they can be seen literally halfway across the universe. They outshine all the stars in the rest of the galaxy combined. The expanding material, called the supernova remnant, forms fantastic shapes. The most famous is the Crab Nebula, from a star we saw blow up in the year 1054. The tendrils form as the material expands into the gas and dust that surrounded the progenitor star. As remnants expand and age, they become more tenuous. Some have bright rims as they push into material between the stars. Others form complex webs of filaments. I'm often asked if there are any stars near enough to hurt us when they explode. The quick answer is no. Even though supernovae are incredibly violent, space is big. A supernova would have to be at least as close as 100 light years from us before we start feeling any real effects. The nearest star that might explode in this way is Spica in Virgo, and it's well over 100 light years away. I say might explode because it's at the lower mass limit for going supernova. It might not explode at all. Betelgeuse will certainly explode someday, but it's too far away to hurt us. We're pretty safe from this particular threat. I'll note that after all this, there is another kind of supernova involving white dwarfs, which we'll cover in our episode about binary stars. Happily, we're probably safe from them too. Breathe easy. As terrifying and dangerous as supernovae are, there's a very important aspect of them you need to know. Supernovae are capable of great destruction, but they're also critical for our own existence. When the star explodes, the gas gets so hot and is compressed so violently by the blast that it undergoes fusion, what astronomers call explosive nucleosynthesis, literally creating heavy elements explosively. New elements are produced in quantities that dwarf the Earth's mass. Calcium, phosphorus, nickel, more iron, all made in the hellish forge of the supernova heat and flung outward into the universe. It takes millennia or longer, but this material mixes with the other gas and dust clouds floating in space. Sometimes these clouds will be actively forming stars. Sometimes the collapse of the cloud to form stars may even be triggered by the supernova slamming into it. Either way, the heavy elements created in the supernova will become part of the next generation of stars and planets. Supernovae are how the majority of heavy elements in the universe are created and scattered. The calcium in your bones, the iron in your blood, the phosphorus in your DNA, all created in the heart of the titanic death of a star. That star blew up more than 5 billion years ago, but parts of it go on in you. Today you learn that massive stars fuse heavy Hey folks, Phil Plait here. In the last episode of Crash Course Astronomy, I talked about the eventual fate of the Sun and other low-mass stars like it. After a series of expansions and contractions, they blow off their outer layers, become white dwarfs, and fade away over billions of years. The end. Except not so much. First, white dwarfs are pretty awesome objects and worth investigating. And second, when a star becomes a white dwarf, it produces what is, quite simply, one of the most gorgeous objects in space. To recap, when the Sun ages, it undergoes a series of changes in its core. It's fusing hydrogen into helium now, today, and will eventually fuse helium into carbon, and it'll make a dash of oxygen and neon too. But when it runs out of helium to fuse, it's in trouble. It doesn't have enough mass to squeeze the carbon nuclei together, so they can't fuse. Fusion is the Sun's energy source. Once the core is nearly pure carbon, that power is switched off. By this time, nearly 8 billion years from now, the sun's outer layers are gone, expelled by all the shenanigans going on in the core. What's left of our star is just its core, exposed to the dark of space. Over the next few billion years, it'll cool and fade to black. That might seem like the end of the story, but I skipped a step, and it's a beauty. When helium fusion stops, the sun's core will have about half the mass of what the sun does today. The rest will have blown away into space around it. What remains is basically composed of electrons and carbon nuclei mixed with a small amount of a few other elements. So what kind of an object are we left with here? You may know that like charges repel. Electrons have a negative charge and repel each other. The tighter you squeeze them, the stronger that pressure. There's also a second force called electron degeneracy pressure. It's a result of some of the weird rules of quantum mechanics. For you QM nerds, it's the Pauli exclusion principle. This describes how subatomic particles behave on teeny scales. One of these rules is that electrons really hate to be squeezed together, above and beyond simple electric repulsion. This resistance is phenomenally strong and becomes the dominant force in supporting the core of a star once helium fusion stops. By the time this electron degeneracy pressure balances the core's immense gravity, the core is only about the size of Earth, 1% the original width of the sun, and it's called a white dwarf. Listing its characteristics is enough to melt your brain. Ironically, everything about it gets amplified as its size shrinks. It becomes ridiculously dense. A single cubic centimeter of it, the size of a six-sided die, has a mass of 1,000,000 grams, 1 metric ton. An ice cream scoop of white dwarf material outweighs 60 cars. Because it's so dense, the gravity at the surface of a white dwarf screams up, easily topping 100,000 times the Earth's gravity. If you have a mass of 75 kilos, you'd weigh 7,500 tons if you stood on the surface of a white dwarf. Not that you can. Stand there, I mean. You'd be flattened into a greasy smear. But not for long. Newborn white dwarfs are hot. They can glow at temperatures of upwards of 100,000 degrees Celsius. If you were on the surface, you'd be a vaporized and ionized smear. Their intense heat makes them white, and they're small, hence their name. They're so hot, they also glow in the ultraviolet, even in X-rays. Weirdly though, because they're so small, they're actually quite faint. The closest one to us, Sirius B, can only be seen with a telescope, even though it's 9 light years away, one of the 10 closest known stars. Over 10,000 white dwarfs have now been found in our galaxy. Still, any gas near a newly formed white dwarf is likely to be affected by the intense radiation pouring out of it. And hey, wait a sec. When a star like the sun is in its final death throes, it expels its outer layers as a gaseous wind. You don't suppose? Yep. By the time that white dwarf forms, the gas blown off hasn't gotten very far from it, at most a light year or two. That's plenty close enough to get zapped by the white dwarf radiation, causing that gas to glow in response. What does something like that look like? Why, it looks like this. This object is what we call a planetary nebula. It's a funny name, and like so many other names, it's left over from when these objects were first discovered. The astronomer William Herschel, the same man who discovered infrared light and the planet Uranus, gave them that name because they appeared like small green disks through the eyepiece. The first planetary nebula was discovered in 1764 by the French astronomer Charles Messier, who spent years scanning the skies looking for comets. He kept seeing faint fuzzy objects that he mistook for comets, so he decided to make a catalog of them, a sort of avoid these objects list. That list is now a staple of amateur astronomers, because ironically it contains some of the best and brightest objects to observe. Among them is M27, the 27th object on Messier's list, one of the biggest planetary nebulae in the sky, and one of my favorites. I love seeing it through my telescope when it's up high in the summer. Planetary nebulae can be a bit tough to observe. Most are small and faint. On film, even with long exposures, they can appear to be little more than disks. For a long time, they weren't thought to be terribly complicated. When a star becomes a red giant and blows off its outer layers, it's rotating very slowly, so the wind should blow away in a sphere surrounding the star. Many planetaries, as we call them for short, are round and look like soap bubbles, pretty much what you expect when you look at an expanding shell of gas. But with the advent of digital detectors, their fainter structures became clearer, and the true beauty of these phenomenal objects was revealed. Some are elongated, some have spiral patterns, some have jets shooting out on either side, some have delicate tendrils streaming away from them. In fact, only a handful of the hundreds known are actually circular. Clearly, there's more to planetaries than meets the eye. If the wind from a star blows off in a sphere, how can planetaries come in all these fantastic shapes? It turns out the real situation is more complicated. as usual. When a star is a red giant, it spins slowly and blows off a dense but slow solar wind. If there's nothing else happening to the star, then that wind will blow outward in all directions, spherically. However, as those outer layers of the star peel away, they expose the deeper, hotter part of the star. The star starts to blow a much faster, though far less dense wind. That wind catches up with and slams into the slower wind. When that happens, you get that idealized soap bubble nebula. But some stars are binary, two stars that orbit very close together. We'll go into detail on them in a later episode. But if the dying star has a companion, they may circle each other rapidly. That will shape the wind, forcing more of it outward in the plane of the star's orbits due to centrifugal force. The overall shape of the expanding gas is flattened like a beach ball someone sat on. When the fast wind kicks in, it slams into that stuff in the orbital plane and slows down. But there's less stuff in the polar direction, up and down, out of the plane. It's easier for the wind to expand in those directions, and it forms huge lobes of material stretching for trillions of kilometers. That's a very common shape for planetary nebulae. But to explain many of the shapes we see, the two stars would have to orbit improbably close. Most binaries aren't that tight. So what can cause these shapes? When I was in graduate school, my master's degree advisor, Noam Soker, came up with a nutty idea. Maybe the stars had planets like in our solar system. If the star expanded into a red giant and swallowed them, it would take millions of years or more for the planets to vaporize. And for all that time, they'd be orbiting inside the star, moving faster than the star itself. Like using a whisk to beat eggs, the planets inside the star would spin it up, causing it to rotate faster, fast enough to explain the shapes of planetaries. That was in the early 1990s. A few years later, the first exoplanets were found, and we saw that massive planets orbiting very close to their stars were common. I suspect this is why we see so many weird and fantastic shapes in planetaries. Their progenitor stars swallowed their planets. So planetary nebulae really may owe their existence to planets. And we come full circle. The glow in a planetary nebula is due to the hot central white dwarf exciting the gas. Most of the gas is hydrogen, which glows in the red. However, a lot of the gas is oxygen. There's not nearly as much oxygen as hydrogen, but kilo for kilo, oxygen glows more brightly than hydrogen due to the atomic physics involved. This oxygen glows green, giving planetaries their characteristic hue. Funny, when this green glow was first analyzed spectroscopically, astronomers couldn't identify the responsible element making it. They dubbed it nebulium, but eventually figured out it was just extremely tenuous oxygen. Other colors can be found too. Nitrogen and sulfur glow red, and oxygen can emit blue as well, all adding to the beauty of these celestial baubles. But these aren't just pretty pictures. The structure, color, and shape of a planetary nebula tells us about the life of the star that formed it. We learn even more about stellar evolution by studying how stars die. Mind you, the gas in a planetary nebula is still expanding, cruising outward from its initial momentum of being thrown off the star. Eventually, the gas expands so much it thins out and stops glowing. That takes a few thousand years. So when you see a planetary nebula, you're seeing a very short snapshot of the life, the death, of a star. And that's why we don't see many. Though there are billions of stars in the galaxy that die this way, this phase is very brief. Enjoy looking at them while you can. And what of the sun? Will it one day in the distant future be at the center of a planetary nebula it expels as it dies? Probably not. When the sun becomes a white dwarf, it most likely won't be energetic enough to make the surrounding gas glow. Most planetaries start off as stars more massive and hotter than the sun. When our sun dies, it'll go quietly and without a lot of visible fanfare. Alien astronomers, if they're out there in 8 billion years, may not even notice. But more massive stars do make quite the spectacle. And if they're really massive, more than about 8 times the sun's mass, they really and truly make a scene when they die. They explode. But that's for next week. Today you learned that when low mass When an 8 to 20 solar mass star ends its life, it does so with a bang. a supernova. And when it's all over, there's a couple of octillion tons of superheated plasma expanding away from the explosion site at a fraction of the speed of light, a whole mess of energy released in the form of light and neutrinos, and a bizarre little ball of quantum nastiness in the center, composed almost entirely of neutrons. The properties of this neutron star are almost as bizarre as things get in the universe. And if it all seems rather alien to you, well, that's okay. For a little while, astronomers wondered if aliens really were behind what they were seeing. No, I'm not saying aliens.
One diaphragm for mankind.
When we last left the core of a high-mass star, it was in a bad way. Milliseconds ago, it was fusing silicon into iron, but now it's collapsing under its own immensely powerful gravity. The collapse takes a fraction of a second, but a lot happens in that fraction of a second. In lower mass stars, the core supports itself via electron degeneracy pressure, the result of a rule in quantum mechanics that says electrons vehemently resist being squeezed together. But even electron degeneracy fails to stop the collapse if the core has a mass more than about 1.4 times the mass of the Sun. That's just too much of a load to bear, and the collapse continues. Under these huge pressures, a funny thing happens. Protons, electrons, and other subatomic particles get smashed together, and they merge to form neutrons. And this happens to almost all of them. When the core collapses down to about 20 kilometers in diameter, it's essentially a ball of neutrons with some protons and electrons here and there that survived, and a crust of normal but highly compressed matter on top. When this happens, yet another effect comes into play. Neutron degeneracy. Like electrons, neutrons resist being squeezed too tightly together, but this time the strength of the pressure is far, far stronger than for electrons. If the core is less than about 2.8 times the Sun's mass, the collapse runs into a wall. It stops. This generates a huge shock wave, which, along with a flood of energetic subatomic particles called neutrinos, blasts outwards, blowing up the star. What's left of the core after the metaphorical smoke clears is a neutron star, one of the most bizarre objects in the universe. Such a star would be extremely weird, or really just extreme. Its mass would be more than that of the entire Sun, all packed into a sphere maybe 20 kilometers across. Now, let's just stop there for a sec and let that sink in. The Sun has a mass 300,000 times the Earth. Imagine packing that all into a ball the size of a small city. Too mind-boggling? Okay, think of it this way. You are mostly empty space. Every atom in your body has a nucleus made of tightly packed neutrons and protons, and electrons whizzing around outside them. If you could magnify an atom to be 100 meters across, the nucleus would be roughly the size of a marble. Imagine all that empty space between the nucleus and the electrons. That's a normal atom. But in a neutron star, all of that space would be filled with neutrons. All of it. Every nook and cranny inside the neutron star has matter in it, all the way down to the scale of an atomic nucleus. This is what gives a neutron star its mind-crushing properties. I'm now going to barrage you with very large numbers, so take a deep breath and you might want to sit down. Neutron stars are ridiculously dense. A single cubic centimeter of neutronium, as neutron star stuff is usually called, has a mass of about 400 million tons. Want some perspective on that number? Well, very roughly, that's the total mass of every single car and truck in the United States. Imagine a couple of 100 million vehicles crushed down until they could all fit inside this six-sided die. That's neutronium. It's so dense that, as far as it's concerned, normal matter is a slightly polluted vacuum. If you set it on the ground, it would fall right through the Earth. Now, anything that dense has a huge gravitational pull. If you were on the surface of a neutron star, well, you'd be very dead, obviously, like immediately, flattened down to a thickness of just a few atoms. And that's because a typical neutron star has a surface gravity 100 billion times stronger than Earth's. I have a mass of about 77 kilos, and here on Earth, I weigh about 170 pounds. On a neutron star, I'd weigh 17 trillion pounds. That's 23,000 times the weight of the Empire State Building. But wait, there's more. In our introduction to the solar system, I mentioned that when you take a spinning object and shrink it, the spin will increase. The usual example is an ice skater drawing in his arms, increasing his rotation until he's a blur. The same is true for the star's core when it collapses into a neutron star. It may have had a very slow spin before the supernova, maybe even taking weeks to spin once. But when it shrinks down to just 20 kilometers across and becomes a neutron star, that rotation will increase by a huge factor. A freshly minted neutron star might spin several times per second. The magnetic field increases as well. A star like the Sun has an overall magnetic strength not too different from the Earth's, but when that core collapses, the strength of the field skyrockets, and a neutron star can easily have a magnetic field several trillion times stronger than the Sun's. That's strong enough to erase your credit card from 100,000 kilometers away. See? Ridiculous. All of these properties are brain-melting. But are they real? Could an object like this really exist? Oh my, yes. The first neutron star was detected in 1965, though not recognized for what it was at the time. A couple of years later, another one was found, and this time was correctly identified as a neutron star. But then things got weird. In 1967, Jocelyn Bell was a graduate student helping build a radio telescope. There was a persistent noise in their data they couldn't seem to fix. Bell studied it night after night, finally figuring out that the pattern wasn't a problem with their data. It was from an actual astronomical object. She had discovered the first known pulsar. What's a pulsar, you ask? Pulsars are neutron stars. In a nutshell, their rapid rotation, coupled with their incredibly strong magnetic fields, launch twin beams of energy away from the star, like the beams from a lighthouse. The beams sweep around as the star rotates, and from Earth, we see this as a pulse, a blip of increased brightness. This pulse can be detected in visible light, radio waves, and even X-rays. The spin of a neutron star is amazingly stable, making these pulses act like a very accurately timed cosmic clock. In 1967, no one could believe a natural object could do this, and this object was half-jokingly given the name LGM-1, Little Green Men 1. Now we know of over 1,000 pulsars in just our galaxy alone, and we know they're the leftover cores of massive stars that exploded. Some spin with periods many seconds or even minutes long. Some are in binary systems. Another normal star orbits them. If they're close enough together, the neutron star can rip material off the other star and feed on it. This increases the pulsar's spin, and we know of a few that have incredibly rapid rotation rates. Some spin hundreds of times per second. These are called millisecond pulsars, and if they spun much faster, the centrifugal force would rip them apart, despite their tremendous gravity. Even after 1,000 years, a pulsar can still be a force to reckon with. There's a pulsar in the center of the Crab Nebula, the remains of a star that exploded to create that supernova remnant. A substantial fraction of the light emitted from the nebula is powered by the pulsar itself. Its fierce output energizes the nebula, causing it to glow brightly, even after a millennium. I'm telling you, thinking about neutron stars makes the hair on the back of my neck stand up. And I haven't even mentioned magnetars yet. Neutron stars are more than just weird little balls of neutrons. They have a crust, probably a few centimeters thick, made of highly compressed but more or less normal matter, squeezed into a kind of highly stiffened crystal state. The magnetic field of the star penetrates this crystalline crust and stretches out for quite a distance. In some neutron stars, the magnetic field is even stronger than usual and can be, get this, a quadrillion times stronger than the Sun's. These uber-powerful neutron stars are given the name magnetars. They're relatively rare. Maybe 10% of all neutron stars are born as magnetars, and they have short lifetimes. The magnetic field is so strong, it acts like the brakes on a car, slowing the neutron star's spin. That spin helps power the magnetic field, so the field weakens as the star slows. But while they're around, magnetars are the most magnetic objects in the universe. And with great power comes great responsibility. If your responsibility is to be one of the scariest objects in the universe. Why? In a neutron star, the crust and magnetic field are locked together, so a change in one affects the other. The crust of the star is under incredible strain due to the intense gravity and rapid rotation. If the structure slips, it can snap, creating a starquake, like an earthquake, but just a wee bit stronger. In an earthquake, huge amounts of energy are released when the Earth's crust shifts and snaps, enough to destroy buildings and quite literally move mountains. But in a neutron star, this effect is multiplied hugely. Remember, the crust is phenomenally dense and the gravity is enormous. If the crust strains and snaps, dropping in the crust, shaking it. This also shakes the magnetic field, which reacts poorly. When the sun's magnetic field throws a tantrum, we get a solar flare, which can be as powerful as billions of nuclear bombs. A magnetar flare dwarfs that into insignificance. It can be trillions of times stronger than a solar flare. In a fraction of a second, a magnetar can release as much energy as the sun gives off in 250,000 years. In 2004, astronomers were stunned when a huge blast of X-rays slammed into orbiting satellites. One of these satellites, named Swift, actually had its detectors saturated with X-rays, even though it wasn't even pointing at the source at the time. The X-rays literally came right through the side of the satellite with such intensity that Swift, which was designed to detect powerful X-ray sources, was momentarily blinded by them. The source of this X-ray burst was quickly determined to be a magnetar called SGR 1806-20, and the effects were incredible. It actually compressed the Earth's magnetic field and partially ionized the Earth's upper atmosphere. Oh, did I mention that this magnetar is 50,000 light years away? That's halfway across the galaxy. That's incredible. At a distance of 500 quadrillion kilometers, its effects were felt more strongly than a powerful flare from the sun. The good news is that there are very few magnetars like this in the galaxy. Probably fewer than a dozen. Also, catastrophic explosions like the one in 2004 are rare. If one had happened any other time in the past 40 years or so, we would have detected it. And frankly, it's really cool that we had astronomical satellites orbiting the Earth which could study it. We've come a long way in understanding neutron stars since they were first discovered, but there's much about them we don't understand. Every time we find out more, we find out they're even weirder than we first thought. And yet, for all that, they're not the weirdest things in the sky. Not by a long shot. That place is held pretty securely by the other type of object created in a supernova, a black hole. Stay tuned. Today you learned that when a star between 8 and 20 times the sun's mass explodes,
So, ladies and gentlemen, this is what we're going to be discussing in this lecture and the upcoming lectures. So I'm just quickly going to use Google Drive slideshow just for the first intro lecture to show you a few animations. Then I will swap to the normal slides again. So for this lecture, we are going to look at the interstellar medium, so making stars from the interstellar medium, young stellar objects and protostellar disks, stellar structure and nuclear fusion, then how that fits together with main sequence stars. So in a previous chapter, you discovered that a wide range of differences within the family of stars. So in this chapter, you will combine observations and hypotheses to understand how nature makes stars and learn the answers to 5 important questions. So I said we've already hit the upload the wrong lecture slides. Let me just quickly check on my side. Now this is the correct slides we are in. So something might sound similar, but this is the correct slideshows. But thank you for checking up. So the first question is how do astronomers study the gas and dust between the stars, called the interstellar medium? Secondly, how do stars from the interstellar medium, how do stars form from the interstellar medium? How do stars remain stable? How do stars make energy? And lastly, why do the luminosities and lifetimes of stars depend on their masses? So the stars are not internal. So when you look at a sky, you see hundreds of points of light. And amazingly enough, each one, like the sun, is a tremendous nuclear fusion reactor held together by its own gravity. So the stars you see tonight are the same stars your parents, grandparents, and great-grandparents saw. Stars don't change perceptibly in a person's lifetime, or even during all human history, but they do not last forever. Stars are born and stars die. So I showed this animation before. So when we think about the death of stars, it's not like the Death Star. It is more something like this. Oh, so you guys are correct. I am sharing the wrong slides. Let me open up the right ones. So my own notes I opened up and the slides I'm sharing are different slides. So this should be the right slides now. Sorry about that. Can you all see these slides? Okay, cool. So for this lecture, we're going to look at giant stars, lower main sequence stars, the evolution of binary systems, and then finally the death of massive stars. So this lecture describes how stars are born and how they resist their own gravity by fusing nuclear fields in their centers to keep their internal pressure high. But they can last only as long as they fuel. So there are 5 important questions we must answer in this lecture. So firstly, what happens to a star when it uses up the last of the hydrogen in its core? Secondly, what evidence shows that stars really evolve? Thirdly, how will the sun die? Fourthly, what happens if an evolving star is in a binary system? And then lastly, how do massive stars die? So, the death of stars is not the Death Star blowing something up. But it is rather something like this. So now I can swap over to the proper slides. So the death of stars are important because life on Earth depends on the sun, but also because the death of massive stars create the atomic elements of which you are made. If stars didn't die, you would not exist. So this is quite an interesting sketch. Here you can see where these different elements are formed. So the yellowish ones is the merging of neutron stars. The brownish ones or dark orange is the dying of low mass stars. The dark blue is exploding massive stars. Light blue is exploding white dwarfs. The red ones is the Big Bang. And then the purple ones is the cosmic ray fusion. So when we are talking about what happens in star life cycles, there are 3 paths that we are going to discuss and what happens. So remember, the star forms in stellar nebula, then it can become an average star. So the size, for example, our own sun is an average star, they'll become a red giant, then a planetary nebula, and end off as a white dwarf. But if we have a star that is 8 solar masses or more, that will form a massive star, then a super red giant, then a supernova. And depending, we're going to discuss that in depth as well, depending on a few things. It will either become a neutron star or a black hole. So gravity is patient. Stars generate tremendous energy resisting their own gravity. But no star has an infinite supply of fuel for its nuclear reactions. So when the fuel runs out, the star dies. So to always keep in mind when we talk about the life cycle of stars, the gravity pulling inwards or pushing down needs to be counteracted by the pressure of the nuclear reactions pushing outward. And that keeps the star stable. And in the previous lecture, we've talked about the temperature pressure thermostat, and that is what keeps the star stable. And until that thermostat is not working anymore, then we're starting to reach the end of a star's life cycle. So occasionally, astronomers see a formerly faint star suddenly appear much brighter in the sky, then fade away after a few weeks or a month. You will learn that what seemingly a new star in the sky is either a nova, an eruption on the surface of a stellar remnant, or a supernova, the violent explosion, explosive death of an aging massive star. So a few novae, plural of nova, are discovered each year, and supernova, or supernovae plural, are so rare that only one or two occur each century in our entire galaxy. But astronomers surveying thousands of galaxies can see many supernovae flare up per year. The mass of a star is critical in determining its fate. Massive stars can die in violent supernova explosions, but lower mass stars die quiet deaths. To follow the evolution of stars to their graves, you can start by following the life story of a sunlight medium mass star as it becomes a giant star. After that, you will learn how stars are different masses in their lives. So I don't know, have you guys been following the super red giant Betelgeuse the last year and a half? So in the last year and a half, Betelgeuse has become exponentially brighter. So usually when we see something like that, we know the star is about to go supernova. But it's brighter, but it looks like it has stabilized for now. But all indications show that it will go supernova. So we don't know exactly when it's going to go boom, but we are still trying to figure that out. So eyes are on Betelgeuse at the moment because it increased its brightness and then it stabilized. So it all depends on how much fuel is left that it's fusing. But we are safe to say that Betelgeuse are at the end of its life. So the massive red supergiant star V838 flared up in 2002. The expanding shell of light from the flare illuminated surrounding gas and dust that was probably ejected from the star in earlier outbursts. So bright spikes are produced by diffraction in telescopes. So these spikes are just a diffraction pattern in telescope. Planetary nebula IC1295 consists of shells of gas expelled by an aging red giant star. The star's remnant can be seen in the center of the nebula, contracting to become a white dwarf. Intense UV radiation from the central star is making the nebula grow. The prominent green color is emissions from ionized oxygen. Plan A near-infrared image of galaxy M82 and supernova 2018J observed from the Stratospheric Observatory for Infrared Astronomy, SOFIA. The other two labeled objects are foreground stars in our galaxy. So this is the infrared image of the galaxy, and this is just stars between us and that galaxy. So in our galaxy is these two stars. The main sequence star generates its energy by nuclear fusion reactions that combine hydrogen to make helium. The period during which the star fuses hydrogen lasts a long time, and the star remains on the main sequence for 90% of its total existence as an energy-generating star. So when the hydrogen is exhausted, however, the star begins to evolve rapidly. So first thing is an average sized star will first expand into a giant star. So nuclear reactions in the main sequence star's core fuse hydrogen to produce helium. Because main sequence stellar cores are cooler than 100 million Kelvin, the helium can't overcome the Coulomb barrier to fuse in nuclear reactions. So it accumulates at a star's center like ashes in a fireplace. Initially, this helium ash has little effect on a star, but as hydrogen is exhausted and the stellar core becomes pure helium, the star loses the ability to generate the nuclear energy that opposes gravity. As soon as the energy generation starts to die down, gravity begins making the core contract, so this making the core more dense. Although the core of helium ash can't generate nuclear energy, it does grow hotter as it contracts because it is converting gravitational energy into thermal energy. The rise in temperatures heat the unprocessed hydrogen just outside the core, hydrogen that was never before hot enough to fuse. Soon hydrogen fusion begins in a spherical layer or shell around the exhausted core of the star. Like a grass fire burning outward from an exhausted campfire, the hydrogen fusion shell creeps inward, leaving helium ash behind and increasing the mass of the helium core. The flow of energy produced by the hydrogen fusion shell pushes toward the surface, heating the outer layers of the star and forcing them to expand dramatically. So in this image, when a star runs out of hydrogen at its center, the core contracts to a small size, becomes very hot, and begins nuclear fusion in a shell, so the blue part of the shell over here. The outer layers of the star start to expand and cool. So the red giant star shown here has an average density much lower than the air at Earth's surface. So here, the solar mass stands for the mass of the sun, and the R0 symbol stands for the radius of the sun. Stars like the sun become giant stars of 10 to 100 solar radii, and the most massive stars become supergiants of 1,000 times larger than the sun. This explains the large diameters and low densities of the giant inserts. The expansion of its envelope really changes the star's location in the HR diagram. Just as contraction heats a star, expansion cools it. As the outer layers of gas expand, energy is absorbed in lifting and expanding the gas. The loss of that energy lowers the temperature of the gas. Consequently, the point that represents the star in an HR diagram moves to the right relatively quickly, so in less than 1 million years for a star that has 5 solar masses. A massive star moves to the right across the top of the HR diagram and becomes a supergiant, while a medium mass like star like the sun becomes a red giant. So here we will see massive stars evolve from the main sequence into the supergiant region. So a star that has 15 solar masses, like Betelgeuse, become a super red giant. So 5 solar mass, super red giant. So here at 3 solar masses, so less massive than stars evolve into the giant region. So here we can see the giant region, and the sun will become a giant star at the end of its lifetime. Is Betelgeuse going to become a black hole? So yes. So the current math and mathematical models we have suggest that Betelgeuse will become a black hole. So as the radius of a giant star continues to increase, its enlarging surface area makes the star more luminous, moving its point upward in the HR diagram. So famous star Aldebaran, the glowing red eye of the Taurus the Bull, is such a red giant with a diameter more than 40 times that of the sun, but a much cooler surface temperature. So if you look at the Orion constellation, we have Pleiades, and here we have Aldebaran. So what happens when the star expands into a giant star? To understand that process, we need to understand degenerate matter. So although the hydrogen fusion shell can force the envelope of the star to expand, it can't stop the contraction of the helium core. Because the core is not hot enough to fuse helium, gravity squeezes it tighter and becomes very small. So while the star is becoming a giant star, the outer layers start to expand and the core starts to shrink. So when gas is compressed to such high densities, it begins to behave in surprising ways that can affect the evolution of a star. To continue the theory of stellar evolution, you need to consider the behavior of the gas at extremely high densities. Normally, the pressure in a gas depends on its temperature. The hotter a gas is, the faster its particles move and the more pressure it exerts. The gas inside a star is ionized, so there are two kinds of particles, atomic nuclei and free electrons. Under normal conditions, the gas in a star follows the same laws relating pressure and temperature as gases do on Earth. But if the gas is just one of two possible directions, two electrons can occupy a single energy level only if they spin in opposite directions. That level is then completely filled, and a third electron can't enter because whichever way it spins, it will be identical to one or the other of the two electrons already in that level. A low-density gas has fewer electrons per cubic centimeter, so there are plenty of energy levels available. If a gas becomes very dense, however, nearly all of the lower energy levels are occupied. In such a gas, a moving electron can't slow down. Slowing down would decrease its energy, and there are no open energy levels for it to drop down to. It can speed up only if it can absorb enough energy to leap to the top of the energy ladder, where there are empty energy levels. So a question, since Betelgeuse is 600 light years away, what are seeing is 600 years old? So surely the effects of Betelgeuse as a black hole can already be felt, or does gravitational waves travel at the same speed? So I'm not quite exactly sure at the speed a gravitational waves travels, but yes, it will take more or less longer. So yes, we're actually looking back in the past. So we are seeing Betelgeuse as it was 600 years ago. So here we will see this is the energy levels of a low density gas, and here is the energy levels of a high density gas with our two electron pairs. So when a gas is so dense that electrons are not free to change their energy, astronomers call it degenerate matter. Although it is a gas, it has two peculiar properties that can affect the star. First, the degenerate gas resists compression. To compress the gas requires pushing against the moving electrons, and changing their motion means changing their energy. That requires tremendous effort because you must boost them to the top of the energy ladder. That is why degenerate matter, though still a gas, is harder to compress than the toughest hardened steel. Secondly, the pressure of degenerate gas does not depend on temperature. To see why, note that the pressure depends on the speed of the electrons, which can't be changed without tremendous effort. The temperature, however, depends on the motion of all the particles in the gas, both electrons and nuclei. If you add heat to the gas, most of that energy goes to speed up the motions of the nuclei, which move slowly and don't contribute much to the pressure. Only a few electrons can absorb enough energy to reach the empty energy levels at the top of the energy ladder. This means that changing the temperature of gas has almost no effect on its pressure. These two properties of degenerate matter becomes important when stars end their main sequence lives. Eventually, many stars collapse into white dwarfs, and you will discover that these tiny stars are made up of degenerate matter. But long before that, the cores of many giant stars become so dense that they are degenerate, a situation that can produce a cosmic bomb. So are you guys happy with the explanation of degenerate matter? Okay, cool. So this, because continuing on now of the lecture, this will become very important. So now we're going to look at helium fusion. So remember, in a star like our sun, we start with hydrogen. Our hydrogen gets fused, so we have our helium ash. The helium ash is making the core contract. So what happens next? So hydrogen fusion main sequence stars leaves behind helium ash. 3 helium nuclei can collide to make a carbon nucleus in what is called the triple alpha process. The nuclear physicists refer to helium nuclei as alpha particles. The helium ash in the core of main sequence stars is too cool to fuse because helium nuclei have positive charges twice that of hydrogen nuclei. So the helium nuclei need to move very fast to overcome that higher Coulomb barrier. As a giant star fuses hydrogen to helium in an expanding shell, its inert core of helium contracts and grows hotter. When the temperature of the core finally reaches 100 million Kelvin, it begins to fuse helium nuclei to make carbon. How a star begins helium fusion depends on its mass. Stars more massive than about 3 solar masses contract rapidly. The helium-rich cores heat up, and helium fusion begins gradually. Less massive stars evolve more slowly, and their cores contract so much that a gas becomes degenerate. On Earth, a teaspoon of the gas would weigh as much as a large truck. In this degenerate matter, the pressure does not depend on temperature, and that means the pressure-temperature thermostat does not regulate energy production. When the temperature becomes hot enough, helium fusion begins to make energy and the temperature rises, but pressure does not increase because the gas is degenerate. The higher temperatures increases the helium fusion even further, and the result is a runaway explosion called the helium flash, in which, for a few minutes, the core of the star can generate more energy per second than does an entire galaxy. Although the helium flash is sudden and powerful, it does not destroy the star. In fact, if you were observing a giant star as it experienced the helium flash, you would probably see no outward evidence of this eruption. The helium core is quite small, and all of the energy of the explosion is absorbed by the distant envelope. In addition, the helium flash is a very short-lived event in the life of a star. In a matter of minutes to hours, the core of the star becomes so hot that a significant number of electrons get boosted to empty energy levels at the top of the energy ladder. That increases the pressure and ends the degenerate conditions. And a pressure-temperature thermostat brings the helium fusion under control. From that point on, the star proceeds to fuse helium steadily in its core. There are 2 reasons why the helium flash is important. Firstly, it is so violent and so sudden that it makes it difficult to compute models of stars and be sure how they evolve. Astronomers have to exercise ingenuity to get past the helium flash and follow the further evolution of stars. Secondly, the helium flash is a good illustration of how science reveals a hidden universe. Astronomers would never have known about the helium flash were it not for the theoretical calculation of stellar models. The Sun will experience a helium flash in 6 to 8 billion years, but stars less massive than about 0.4 solar masses never get hot enough to ignite helium. Stars more massive than 3 solar masses ignite helium before their contracting cores become degenerate. So here we can see when a main sequence star exhausts the hydrogen in its core, it evolves rapidly to the right in the HR diagram as it expands to become a cool giant. It then follows a looping path as it fuses helium in its core and then fuses helium in a shell. So compare with figure 10.3, it's evolutionary track adapted from the artwork beginning of this chapter. So here we can see we have our star leaving, becomes supergiant. Then we have the helium flash, and it begins to fuse helium. So helium fusion produces carbon, and some of the carbon nuclei absorb helium nuclei to form oxygen. A few of the oxygen nuclei can absorb helium nuclei and form neon and then magnesium. Some of these reactions release neutrinos, which, having no charge, are more easily absorbed by nuclei to gradually build even heavier nuclei. These reactions are not important as energy producers, but they are a slow cooker process that forms small traces of heavier elements right up to bismuth with atomic weight of 209. Nearly 4 times heavier than iron. So many of the atoms in your body were produced this way. As the helium fuel is used up, the accumulation of carbon and oxygen atoms creates an inert core to cool to fuse. Once again, the core contracts and heats up, and soon a helium fusion shell ignites below the hydrogen fusion shell. Now that a star makes energy in 2 fusion shells, it quickly expands and its surface cools once again. The point that represents the star in the HR diagram moves back to the right, completing a loop. What happens to a star after helium fusion depends on its mass. But no matter what tricks the star plays to delay its end, it can't survive long. It must eventually collapse and end its career as a star. So now we're going to start discussing star clusters, and we use star clusters as evidence of evolution. So, just as Sherlock Holmes studies peculiar dust on a lampshade as evidence that will solve a mystery, astronomers look at star clusters and say, aha, a photo of a star cluster freezes a moment of the evolution of the cluster and makes the evolution of stars visible to human observers. So in a star cluster, because all stars in a cluster formed nearly simultaneously from the same gas cloud, the stars in a cluster have about the same age and composition. So any differences you see among them are due to their differences in mass. That means that when you look at a cluster, you can see the effects of stellar evolution as it acts on otherwise similar stars of different mass. So there are 3 important aspects of star clusters. Firstly, there are 2 kinds of star clusters, open clusters and globular clusters. They look different, but they are similar in the way their stars evolve. You can estimate the age of a star cluster by observing the turn-off point in a distribution of the points that represents its stars in the HR diagram. And then lastly, finally, the shape of a star cluster's HR diagram is governed by the evolutionary paths for the stars take. The HR diagrams of all the clusters are especially clear in outlining how stars evolve away from the main sequence to the giant region and then move left along the horizontal branch before evolving back into the giant region. By comparing clusters of different ages, you can visualize how stars evolved almost as if you were watching a film of star clusters evolving over a billion years. Contracting stars heat up by converting gravitational energy to thermal energy. Low mass stars have little gravitational energy, so when they contract, they don't get very hot. This limits the fields they can ignite. In the previous chapter, you saw that protostars less massive than 0.08 solar mass can't get hot enough to ignite hydrogen. This section will concentrate on stars more massive than 0.08 solar mass, but no more than a few times the mass of the Sun. Structural differences divide the lower main sequence stars into 2 subgroups, very low mass red dwarfs and medium mass stars such as the Sun. The critical difference between the 2 groups is the extent of interior convection. If the star is convective, fuel is constantly mixed, and its resulting evolution is drastically altered. So let's talk about red dwarfs. So stars between 0.08 and about 0.4 solar mass, the red dwarfs, have two advantages over more massive stars. So firstly, they have very small masses, and that means they have very little weight to support. So their pressure temperature thermostats are set to low, and they consume the hydrogen field very slowly. The red dwarfs has a second advantage in that they are totally convective. That is, they are stirred by circulating currents of hot gas rising from the interior and cool gas sinking inward. This means the star is mixed like a pot of soup that is constantly stirred as it cooks. Hydrogen is consumed uniformly throughout the star, which means the star is not limited to the fuel in its core. It can use all of its hydrogen, prolonging its life on a main sequence. Because a red dwarf is mixed by convection, it can't develop an inert helium core surrounded by unprocessed hydrogen. Therefore, it can never ignite the hydrogen shell and can't become a giant star. What astronomers know about stellar evolution indicates that these red dwarfs should use up nearly all of their hydrogen and live very long lives on the lower main sequence, surviving 400 billion years or more. Of course, astronomers can't test this part of their theories because the universe is only 13.8 billion years old. So not yet a single red dwarf has died of old age anywhere in the universe. Every red dwarf that has ever been born is still shining today. So as we discussed in previous lectures, we can classify our red dwarfs in three subcategories: L dwarfs, T dwarfs, and Y dwarfs. Stars like the Sun eventually become hot enough to ignite helium as they pass through their giant phase. But if they contain less than 4 solar massive, they do not get hot enough to ignite carbon, the next fuel after helium. When they reach that M phase, they collapse and become white dwarfs. There are two keys to evolution of these Sun-like stars that lack of complete mixing and mass loss. The interiors of medium mass stars are not completely mixed. Stars of 1.1 solar masses or less have no convection near their centers, so they are not mixed at all. So stars with masses greater than 1.1 solar masses have small zones of convection at their centers, but this mixes no more than about 12% of the star's mass. So medium stars, wherever they have convective cores or not, are not thoroughly mixed, and the helium ash accumulates in an inert helium core surrounded by unprocessed hydrogen. So inside main sequence stars, the more massive stars have small convective interiors and radiative envelopes. So stars like the Sun have radiative interiors and convective envelopes. The lowest mass stars are convective throughout. The cores of the stars when nuclear fusion occurs, are not shown here, are small proportions of the interior. So now it's starting to become a planetary nebula. So when a medium mass star like the Sun becomes a distant giant, its atmosphere cools. As it cools, it becomes more opaque, and light has to push against it to escape. At the same time, the fusion shell becomes so thin they are unstable and begin to flare, which also pushes the atmosphere outward. Because of this outward pressure, an aging giant can expel its outer atmosphere in repeated surges to form one of the most intriguing objects in astronomy, a planetary nebula. So called because through a small telescope it looks like the greenish-blue disk of a planet like Uranus or Neptune. In fact, a planetary nebula has nothing to do with a planet. It is composed of ionized gases expelled by a dying star. So here we can see our white dwarf in the center and our outer layers of the star's atmosphere that has been pushed away. Here again we can see the white dwarf in the center and ionized gas that has been pushed away from the star. So there are 4 important points on planetary nebula. Firstly, you can understand what planetary nebula are like by using simple observation principles such as Kirchhoff's laws and the Doppler effect. And secondly, notice the model that astronomers have developed to explain planetary nebula. The real nebula are more complex than the simple model of a slow wind and a fast wind, but a model provides a way to organize the observed phenomena. Thirdly, oppositely directed jets, so much like bipolar flows from protostars, produce many of the asymmetries seen in planetary nebula. And then lastly, the star itself must contract into a white dwarf. So what exactly are white dwarfs? So when you survey the stars, you discovered that white dwarfs are the second most common kind of star. Only red dwarfs are more abundant. Now you can recognize the billions of white dwarfs in a galaxy as the remains of medium mass stars. The first white dwarf discovered was the faint companion to famous star Sirius. In that visual binary system, the bright star Sirius A, the white dwarf Sirius B, is 9,000 times fainter than the famous star Sirius A. The orbital motions of the stars reveal that a white dwarf contains 0.98 solar mass, and its blue-white color tells you its surface is hot, about 45,000 Kelvin. So when you survey the stars, you discover that white dwarfs are the second most 9,000 Kelvin. So the orbital motions of the stars reveal that a white dwarf contains, it's about 45,000 Kelvin, because it is both very hot and very low luminosity. It must have a small surface area. In fact, it's about the size of Earth. Dividing its mass by its volume reveals that it's very dense, about 2 times 10 to the power 6 grams per cubic centimeter. On Earth, a teaspoon of Sirius B material will weigh more than 10 tons. A normal star is supported by energy flowing outward from its core. But a white dwarf can't generate energy by nuclear fusion. It has exhausted its hydrogen and helium fuels and converted them into carbon and oxygen. When a star collapses into a white dwarf, it converts gravitational energy into thermal energy. Its interior becomes very hot, but it can't get hot enough to fuse its carbon-oxygen interior. Instead, the star contracts until its core becomes degenerate. Although a tremendous amount of energy flows out of the hot interior, it is not the energy flow that supports the star. The white dwarf is supported against its own gravity by the pressure of its degenerate electrons. A white dwarf's future is bleak. As it radiates energy into space, its temperature gradually falls, but it can't shrink any smaller because its degenerate electrons resist getting closer together. Degenerate matter is a very good thermal conductor. So as heat flows to the surface and escapes into space, the white dwarf gets fainter and cooler, moving downward and to the right of the HR diagram. Because a white dwarf contains a tremendous amount of heat, it needs billions of years to radiate that heat through its small surface area. Eventually, such objects may become cold and dark, so-called black dwarfs. Our galaxy is not old enough to contain a black dwarf. The coolest white dwarfs in our galaxy are about the temperature of the Sun currently. So perhaps the most interesting thing astronomers have learned about white dwarfs has come from mathematical models. So the equations predict that if you add mass to a white dwarf, its radius will shrink because added mass will increase its gravity and squeeze it tighter. If you add enough to raise its total mass to about 1.4 solar masses, the equations predict that its radius will shrink to 0. This is called the Chandrasekhar limit of the Subramanian Chandrasekhar, the astronomer who discovered it. So here we will see our normal star with radius and mass. So if we add more mass onto that degenerate material and we get to about 1.4 solar mass, something weird happens. And you guys know where this is leading up to. Yes, to black holes. So here we can see remnants of these black holes. So here in this image, this is Thor's helmet. So stars in a binary system can evolve independently of each other. So if their orbits are large. In this situation, one of the stars can swell into a giant and collapse without disturbing its companion. But some binary stars orbit as close to each other as 0.1 AU. When one of these stars begins to swell into a giant, its companion can be strongly affected. These interacting binary stars are interesting in their own right. The stars share a complicated history and can experience strange and violent phenomena as they evolve. But such systems are also important because they can help astronomers understand the ultimate fate of stars. In the next chapter, you will see how astronomers search for black holes in interacting binary systems. So what happens is mass transfer. So binary stars can sometimes interact by transferring mass from one star to the other. The gravitational fields of these two stars, combined with the rotation of the binary system, define a dumbbell-shaped volume around a pair of stars called the Roche lobes. The surface of this volume is called the Roche surface. So here we have the two stars. So here we will have one Roche lobe, and here we will have the other Roche lobe. Everyone's still following and understanding? Awesome. So the size of the Roche lobes depends on the masses of the two stars and the distance between the stars. If the stars are far apart, the lobes are very large, and the stars can easily retain their own material. If the stars are close together, however, the lobes are small and can interfere with the evolution of the stars. Matter inside each star's Roche lobe is gravitationally bound to the star, but matter that leaves a star's Roche lobe can fall into the other star or leave the binary system completely. So looking at this sketch, there's something interesting that I'm going to show you now. So have you guys ever learned about Lagrange points? Have you learned it in one of your courses yet, or haven't you touched on it before? So yes, so in essence, somewhere in classical mechanics, so other word is Newtonian mechanics, but I prefer the word classical mechanics, you are going to learn about Lagrangian mechanics. Have you learned about Lagrangian mechanics? Okay, so I thought so because you usually do it in second year when you have the appropriate calculus. But what's Lagrangian mechanics is nice. So say, for example, you need to solve a system of equations. The rule of thumb normally is for each variable you need an equation. So say, for example, you have a large system and you have 30 variables. That means you need 30 different equations to solve those variables. So in Lagrangian mechanics, you look at your system and you look at different points where your system is moving. So for example, the best system usually is if you have a seesaw. So a seesaw only has one point where everything is moving. So for each place in your model or your system that has a point where you can move around, that is, you create an equation for that, a differential equation. And then you solve all the differential equations to points where those points or places of movement will be stable. So that means nothing will interact on that point. And that point where the system is stable is called your Lagrange points. So that's why the James Webb Telescope is at L2. So that means Lagrange point 2. So that means that's the second point in the system where it will be stable. So meaning there won't be any interactions from gravity, or it will cancel each other out. So the same principle here, we have our different Lagrange points. So around our diagram here, we will have our inner Lagrange point, or L1, L4, L2, L5, and L3. So the Lagrange points are planes in an orbital plane of a binary star system where a bit of matter can reach stability. For astronomers, the most important of these points is the inner Lagrange point where the two Roche lobes meet. So something interesting for continuing about Lagrangian mechanics. So Lagrangian mechanics makes it very, very, very easy to solve for different systems, but it is very mathematically inclined, so usually do triple integrals or triple differentiation, but it is very powerful and makes it much nicer. So I know in second year, probably if you're in the classical mechanics course or in a calculus course or applied math course, they will ask you to solve a motion problem. A motion problem, for example, you throw a ball off a building and you have to solve it with classical mechanics, and you have to solve it making use of Lagrangian mechanics. Usually in that system where you use normal Newtonian physics, you would be able to solve it in about 4 or 5 lines of calculation, but in Lagrangian mechanics, you should be able to solve it in 2 and 3 lines of mathematics with much less variables. So yes, multivariable calculus. So in general, there are only 2 ways matter can escape from a star and reach the inner Lagrange point. The first one is, if a star has a strong stellar wind, some of the gas blowing away from it can pass through the inner Lagrange point and be captured by the other star. And then secondly, if an evolving star expands so far that it fills the Roche lobe, which can occur if the star are close together and the lobes are small, then matter can overflow through the inner Lagrange point onto the other mass. So mass transfers driven by stellar wind tends to be slow, but mass can be transferred rapidly by an expanding star. So mass transfer between stars can affect the evolution of the stars in surprising ways. In fact, it is the solution to a problem that puzzled astronomers for many years. In some binary systems, the less massive star becomes a giant, while the more massive star is still a main sequence. If higher mass stars evolve faster than lower mass stars, how do lower mass stars in such a binary manage to leave the main sequence first? So this is called the Agile paradox of the binary system Agile. So yes, the Agile paradox explains. So this paradox can be estimated by mass exchansion. So the 0.8 solar mass subgiant star used to be the more massive of the 2 stars. So when the Agile binary formed, it was a 3 solar mass main sequence star with a 1.5 solar mass main sequence companion. So as the 3 solar mass star evolved into a red giant, tidal forces began to deform the star, and the surface got close enough to the other stars so that gravity pulled matter from one onto the other. So here we can see the matter is being pulled from one onto another. So as a result of mass exchange today, the giant lost 2.2 solar mass and shrunk into a subgiant star, while the companion star is now a 3.7 solar mass star. So mass transfer explains how this could happen. Imagine a binary system that contains a 5 solar mass star and a 1 solar mass companion. The 2 stars formed at the same time, so the higher mass star evolving faster leaves the main sequence first. When it expands into a giant, however, it folds its Roche lobe and transfers matters to the low mass companion. The higher mass star loses mass and evolves into a lower mass star, and the companion gains mass and becomes a high mass star that is still on a main sequence. That is the reason why there could be a system such as Agile that contains a 5 solar mass main sequence star and a 1 solar mass giant. So this is what happens in an evolution of a closed binary system. So here we have star A and star B. So star B is more massive than star A. So star B becomes to expand and becomes a giant, and it fills its Roche lobe, and it loses its mass to star A. So then star B loses more mass, and star A gains more mass. And then eventually star A is a massive main sequence star with a lower mass giant companion, and this is what happens in the Agile system. And then we can see then what happens is from there on, then star A becomes a giant star again, and it fills its Roche lobe, and then it starts giving back material to star B. So at what point does this Agile paradox reach equilibrium? So it won't reach equilibrium. So for this is it will start passing mass from one star to another until it reaches a point where none of these two stars can fuse fuel anymore. Because remember, while the system is going on, you are still in a fusion process. So what's happening here is, so either those two will become neutron stars and the neutron stars will collide and that will cause gravitational waves, or depending on where they stop fusing and become neutron stars, become pulsars, become black hole, but it all depends on the mass of these two stars and what happens at the end of their life when they stop fusing. But this process of sharing mass back and forth can prolong the life of these two stars. So now we're going to touch on accretion disks. So matter flowing from one star to another can't fall directly onto the star. Rather, because of conservation of angular momentum, it must flow into a whirling disk around the star. So this is an accretion disk. So the mass will leave the Roche lobes and will form a spinning disk around the other star called an accretion disk. So angular momentum refers to the tendency of a rotating object to continue rotating. All rotating objects possess some angular momentum, and in the absence of an external force, an object maintains its total angular momentum. An ice skater takes advantage of conservation of angular momentum by starting a spin slowly with the arms extended and then drawing them in. As her mass becomes concentrated closer to the axis of rotation, she spins faster. So the same effect causes the slowly circulating water in a bathtub to spin in a whirlpool as it approaches the drain. So here we can see a skater demonstrates conservation of angular momentum when she spins faster by drawing her arms and legs closer to her axis of rotation. So mass transferred through the inner Lagrange point in a binary system towards a star must conserve its angular momentum. If the star is small enough, as in the case of a white dwarf, the mass will form a rapidly rotating whirlpool called an accretion disk. Two important things happen in an accretion disk. First, the gas in a disk grows very hot due to friction and tidal forces. The disk also acts as a brake, shifting angular momentum outward in the disk and allowing the innermost matter to fall into the white dwarf. The interior parts of an accretion disk around a white dwarf are violent places. The temperature of the gas can exceed 1,000,000 Kelvin, causing the gas to emit X-rays. And the matter falling inward can produce a vast explosion when enough accumulates on a white dwarf. The explosion of this material hardly disturbs the white dwarf and its companion star. Mass transfer quickly resumes, and a new layer of fuel begins to accumulate. How fast the fuel builds up depends on the rate of mass transfer. You can expect novae to repeat each time an explosive layer accumulates. Many novae take thousands of years to build an explosive layer, but some only take decades. Now we're going to start talking about novae. So at the beginning of this chapter, you read that the word nova refers to what seems to be a new star appearing in the sky for a while and then fading away. Modern astronomers know that a nova is not a new star, but an old star flaring up. After a nova fades, astronomers can photograph the spectrum of the remaining faint point of light. Invariably, they find a short period of spectroscopic binary containing a normal star and a white dwarf. So nova is evidently an explosion involving a white dwarf. Nova explosions occur when mass transfers from a normal star through the inner Lagrange point into an accretion disk around a white dwarf. As the matter loses its angular momentum in the inner accretion disk, it settles onto the surface of the white dwarf and forms a layer of unused nuclear fuel, mostly hydrogen. As the layer deepens, it becomes denser and hotter until the hydrogen fuses in a sudden explosion that blows the surface of the white dwarf. Although the expanding cloud of debris contains less than 0.001 solar mass, it is hot, and its expanding surface area makes it very luminous. Nova explosions can become 100,000 times more luminous than the Sun. As the debris cloud expands, cools, and thins over a period of weeks and months, the nova fades from view. So here we can see Nova T Praxedes erupted about 2 decades ago, spelling shells of gas into space that this Hubble Space Telescope shows in detail. The shell consists of knots of excited gas that presumably form when a new shell collides with a shell from a previous eruption. Note that this is the system depicted in Figure 1012 in the artist's impression. Its name designated the third variable star discovered in the constellation Praxedes, so in other words, translated, the compass. So what would happen to Earth? What will be the end of Earth? So astronomy is about us. Although this chapter has discussed the deaths of stars, it also has been discussing the future of our planet. The Sun is a medium mass star and must eventually die by becoming a giant, possibly producing a planetary nebula and collapsing into a white dwarf that will spell the end of Earth. Mathematical models of the Sun suggest it may survive as an energy-generating star for an additional 8 billion years, but it is already growing more luminous as it fuses hydrogen to helium. In a few billion years, it will exhaust hydrogen, and its core and swells into a giant star about 100 times its present radius. That giant Sun will be about as large as the orbit of Earth. So, that will mark the end of our world. Whenever the expanding Sun becomes large enough to totally engulf Earth, its growing luminosity will certainly evaporate Earth's oceans, drive away the atmosphere, and even vaporize much of Earth's crust. While it is a giant star, the Sun will lose mass into space. This mass loss is a relatively gentle process, so any cinder that might remain of Earth will not be disturbed, although its orbit will grow larger as the Sun's mass decreases. If anything is left of Earth after the Sun becomes a giant, he will witness the Sun's final collapse into a white dwarf. So this is from mathematical models that will predict what happens. So in 7.588 billion years from now, the Sun have already lost 0.9 solar mass, and it will grow more larger, so engulfing Venus. In about 7.59 billion years, the Sun is a red giant and has 0.8 solar mass, and its orbit will engulf Earth. So this is presumably what will be the end of Earth. So you've seen that low and medium mass stars die relatively quietly as they exhaust hydrogen and helium, and then drive away their surface layers to form planetary nebula. In contrast, massive stars live spectacular lives and then destroy themselves in violent explosions. So right now we have discussed the stellar nebula, how a star is born, the average star, the red giant, the planetary nebula, and a white dwarf. And we've also discussed the massive star that will become a red supergiant, and that will, now what we're going to discuss now is that will become a supernova instead of a planetary nebula. Then it will either become a neutron star or a black hole. Do you guys have any questions still following? You guys still there? You sleeping? Okay, cool. So you guys are still awake. So now we're going to start discussing the nuclear fusion in massive stars. So stars on the upper main sequence have too much mass to die as white dwarfs, but their evolution begins much like that of their lower mass cousins. They consume the hydrogen in their cores and ignite hydrogen shells. As a result, they expand into giants, or for the most massive stars, supergiants. Next, their cores contract and fuse helium, first in the core and then in a shell, producing a carbon-oxygen core. Unlike medium mass stars, the massive stars do become hot enough to ignite carbon fusion at a temperature of about 1 billion Kelvin. Carbon fusion produces more oxygen and neon. As soon as the carbon is exhausted in a core, the core contracts and carbon ignites in a shell. This pattern of core ignition and shell ignition continues with fuel after fuel, and the star develops the layered structure as shown in the following figure. So here we will have our core, then outside the core we will have our different fuels. So the elements in fusion, we have our hydrogen core, helium core, carbon core, neon core, silicon core, until we reach iron. With hydrogen fusion, the shell above the helium fusion shell, above a carbon fusion shell, above and above and above and so on. So after carbon fuses oxygen, neon and magnesium fuse to make silicon and sulfur, and then the silicon fuses to make iron. The fusion of these nuclear fuels goes faster and faster as the massive star evolves. Recall that massive stars must consume their fuels rapidly to support their great weight. But other factors also causes the behavior of fuels like carbon, oxygen, and silicon to fuse at increasing speeds. So hydrogen core fusion can last 7 million years in a 25 solar mass star, but that same star will fuse oxygen in its core in 6 months and silicon in a day. So here we can see the heavy element fusion in a 25 solar mass star. So helium will take about 300 years. There's hydrogen, helium, so no, this is a bad figure, so I can't really see if this is 0.4, but this comes out of the textbook. So here we can see for a solar mass star, hydrogen to helium will take 7 billion years. Helium to carbon will take about 700,000 years. Carbon to oxygen, 600 years. Oxygen to silicon, 6 months. Silicon to iron, 1 day. And then a core collapse in a quarter of a second. So now we're going to talk about supernova explosions of massive stars. So theoretical models of evolving stars combined with nuclear physics allow astronomers to describe what happens inside a massive star when the last of its nuclear fuels are exhausted. The death of a massive star begins with iron nuclei and ends in cosmic violence. So iron will never fuse to form a heavier element, no matter how much it is compressed or energy input there is. So yes, sometimes it can happen. So what we will discuss now in supernova explosions, heavier elements are formed. So as a star develops an iron core, energy production begins to decline, and the core contracts. For nuclei less massive than iron, such contraction heats the gas and ignites new fusion fuels. But nuclear reactions involving iron remove energy from the core in two ways. So first, iron nuclei begin capturing electrons and breaking into smaller nuclei. The gas is so dense it is degenerate, and the degenerate electrons help support the core. The loss of some of the electrons allow the core to contract even faster. Second, temperatures are so high that the average photon is high energy gamma ray, and these gamma rays are absorbed by atomic nuclei, causing them to break into smaller fragments. The removal of the gamma rays heavy also allows the core to contract even faster. Although the core of the star can't generate energy by nuclear fusion, it can draw on the tremendous energy stored in its gravitational field. As the core contracts, the temperature shoots up, but it's not enough to stop the contraction, and the core of the star collapses inward in less than a tenth of a second. The collapse of the core produces an immense supernova explosion in which the star's outer layers are blasted outward. The core of the star must quickly become a neutron star or a black hole, so the subjects of the next chapter. So here we can see the core of a massive supergiant has begun to collapse at the lower left corner. Matter continues to fall inward, so the blue and green as the core expands, and outward yellow, creating a shock wave. To show the entire star at this scale, this page would have to be 30 kilometers in diameter. So only about 0.4 seconds after beginning violent convection in expanding core, so red, pushes outward. So the shock wave will blow the star apart as the neutron star forms at the extreme lower left corner. And then this, we are left with a supernova remnant. So ladies and gentlemen, before we start to classify different supernovas, I think we're going to continue with this lecture tomorrow night. They have said there's 4 minutes left of class. So you have no questions, then you are more than welcome to log off. Just a bit of admin, I will be on campus tomorrow for consultation, so you are more than welcome to come for consultation sessions tomorrow. Otherwise, have a wonderful evening. If I don't see you tomorrow during consultation, then I will see you tomorrow night in class. I will remain active for another minute or two of your questions, but otherwise have a great evening. So questions. So, sir, which spectroscopy do you quickly relate to study the characteristics of the terrestrial body? Visual, radio, infrared. I use radio. Okay, so someone had their hand risen as well. So where and what time are the consultations? So it will be in my office tomorrow. So it's Natural Science Building 1, 5th floor Physics Department, Office 68. So it's National Science Department, floor 5, Office 68. I will be there from around about 10 o'clock tomorrow morning to 3 o'clock tomorrow afternoon. You are more than welcome to pop in anytime during those times. So let me type it in. It's office 5th floor, office 68. So it's Natural Science Building 1, office 568. Pleasure, guys. So if you have no further questions, then I'm also going to log off. So have a wonderful evening, everyone, and I will see you all tomorrow.